So, hello everybody. I think we can start now the workshop. So, I'm Jose Vera from Acciona. I'm the manager of the concrete group at our technological center. I just want to welcome you. Thanks for coming to this workshop. The workshop is build a fully recycled house. Yes, we can. And it deals with recycled materials, RCT, and well, this workshop is being organized in the framework of the RE4 Project, which is funded by European Commission. So thanks for the European Commission to give us this opportunity to devote our efforts to this type of technologies, which are quite important for the future, for sustainability. Well, in this workshop we have expert from outside the project, so thanks for them to be able to give us these talks, and also we will have internal speaker from our project. Then you will have the opportunity to know RE4 Project deeply. Well. I just want to say that this event is being streaming live, so it's being broadcast. So please, I know that this room is not too big, and you can hear me without the mic probably, but please use the microphone in order to be able to be, to have a good sound in the broadcast. So I don't want to say nothing more. So please, Susana.
Hello everyone, my name is Zuzana Tatyakova. I'm from Phoenix TNT. I will be presenting the speakers of today's workshop. I work for Phoenix TNT, which is the dissemination and exploitation leader in the I RE4 project. And we can jump straight into the program of the workshop. There will be slight changes from the one you have received. The presentation potential of recycled building material is unfortunately cancelled. And in the session Circular Economy in Practice, the presentation by Andrea Klinge, she has some issues with her transport from Berlin. There are some strikes or something. So hopefully she will come later in the evening or in the afternoon. So the presentation will be on. So let's start with the first presentation about concrete and the challenge of low carbon, sustainable and circular construction by Alessio Rimoldi, who is the Secretary General at BIBM, European Federation for Precast Concrete. The floor is yours.
Thank you, Susanna. Yeah, sorry. This one, yeah. Okay. So, as Susanna said, my name is Alessio Rimoldi, and I work for BIBM, which is the Federation of the European Precast Concrete Industry. BIBM is not a partner of this project, but we are part of the external interest group, and we are very pleased to be here because our industry is very much interested in all these kind of developments that want to steer out from the linear economy to the circular one. So thank you very much for inviting me to participate to this workshop, and as a starting speaker, I would like to, oops, too fast, to talk about the challenges of low carbon, sustainable and circular construction. That's how our industry see the construction challenges for 2050. I could talk about hours about this, but lucky for you, I only have 15 minutes. As I say, this is how we see today in 2020 the construction in 2050. Just to to be clear, when we go back, for example, only 20 years ago, and we look and how we saw the construction in 2050, we only consider energy efficiency. 10 years later, for example, consideration about environment and the social part enter into the equation, and we start talking about sustainability more and more. Today we are here, and tomorrow we don't know. So we are now working on how we see today construction 2050, but maybe we have to be flexible enough to see that in 10 years, 20 years time, this may change. So why our industry has identified this three driver? Because we believe that in 2050 this is how construction will have to be. And actually, I would say not by chance, because I think that we also we have a common view on it. In December, the European Commission issued the Green Deal from Ursula von der Leyen, and this is a strategy indeed aimed at 2050. It's for the whole economy, but indeed construction play a key role there. It is clearly said that building in an energy and resource efficient way will be a must for 2050, and amongst other more horizontal topics, we have clean and circular economy and zero pollution. But what is the Green Deal, and what is the link between the Green Deal and this three driver? So Green Deal is a growth strategy. So we are talking about how the economy and the future of Europe will develop. That aims to transform EU into a fair and prosperous society. So people at the center of it. With a modern, resource-efficient and competitive economy. Economy is always put there as a way to achieve other objectives, and we will see also later on. When there are no net emission of greenhouse gases in 2050, and that's where the low carbon is. Economic growth is decoupled from resource use, and that's what the circular is. And when you consider the social, the economic, and the environmental aspects, you can say that this is what means sustainable. Now, what does low carbon mean? How do we see the low carbon? Well, we know that if you go on like business as usual today, the greenhouse gases emission will keep on growing for some other years at a low pace, but that is definitely not acceptable. We all know that if we want to achieve the 2 degrees or the 1.5 degrees maximum increase in temperature, we cannot live with this. So the first, how to achieve low carbon, it's made in 2 steps. First one is mitigation technique. That is to say, producing the same or even more, but with much less impact in terms of greenhouse gas emissions. Sometimes I use greenhouse gas, sometimes I use CO2. We know that CO2 is approximately 70% of the impact in greenhouse gases. So the two, I speak about the two at the same time. But there will still remain a part of impact of greenhouse gas emission in the economy. All human activities have this impact. What is necessary is a second approach, is a second step, which will bring the removal of the excessive carbon with carbon removal technologies like very simply planting trees, or carbon capture technology, carbon capture and storage, carbon capture and use. So by doing this, by coupling these two approaches, we can hope to achieve the net zero emissions by 2050. When we talk about sustainability, I think that if I ask what is sustainable construction here in the room, I would get 40, 50 different answers. Someone can be much more focused on the environmental one. Others has a more comprehensive approach. From my point of view, I think I have quite a, I don't know if you can say an engineering approach, very squared approach. Starting from what are the user needs and the technical requirement, develop a sustainable building means, or a sustainable construction means focusing on the 3 pillars, the social, the environmental and economic, in the same way and the same time. You can't focus only on one if you want to really achieve a sustainable building. And this must be a holistic approach, that is to say, considering the whole construction work during the whole life cycle. And finally, as I mentioned before, and that we have seen also in the Green Deal, circular, where does the circular comes from? The circular comes from the idea of decoupling economic growth from resource use. It's not me who say that. That is coming from the United Nations Environmental Panel. It's the resource chapter. Let's make a first assumption. We want that human well-being will increase with time. We want that our children and our grandchildren will live in a better place than we do today. Let's also make the hypothesis that economic activity can be somehow an indicator of this well-being. Now, in order to achieve this decoupling, we need to do two steps. The first one is resource decoupling. That is to say, even if we want an economic activity that is increasing, the use of resources should increase in a way, at a lesser extent than the economic activity itself. But this is not sufficient because we also need to reduce the environmental impact that this economic activity, that this resource use has in the future. You also probably have already seen this idea of circular economy from the Ellen MacArthur Foundation, where the full ecosystem is considered. And you see that you have an input in the case of mining and mineral materials, you have an input of resources. And then what you do is to try and keep all these resources as much as possible in the cycle. It's not only a matter of producing, recycling, and entering again. It's really a matter of keeping everything in the ecosystem as much as possible, minimizing the input of material, minimizing the input of energy, and minimizing the output of material. What does it mean? That is, first thing for me in a circular economy, especially in construction, when we are talking about years, 50 years, 100 years, it's ensure as a service life as long as possible. If you can keep the product, the system working as long as possible, this is the best way to achieve a circular economy. Several internal processes with lower energy need, repair and maintain, for sure, require less energy than, for example, recycling or reuse. But we also have to avoid exiting on the system, and that's where the reuse and the recycling enter in the equation. Now, coming to concrete, this is for me what our industry see as challenges, and how is our industry positioning about it. Well, you have to know that concrete is the second most used material in the world after water, and the third one if you consider also air. That's because concrete is really vital. It's present in our everyday life, in living, working, traveling, public space, private space, infrastructures, and it is probably there so used because it has so many intrinsic properties at an affordable price that makes it the most used construction material in the world. But we are, as I said, we are talking about low carbon. What are the solutions? Well, one could say a very simplistic solution, let's get rid of the binder. We know that in concrete, cement is probably the material with the highest impact in terms of carbon emissions. And indeed, there are already studies working in this direction. For example, the use of geopolymers, the use of alternative binders based on slag, fly ashes, and other material than limestone. But we believe that replacing cement is not the option for different reasons. The first one is the availability of alternative binders. For example, I mentioned fly ash. Fly ash comes from coal. Coal will probably be phased out in the future. Slag also. And also there is the question about the long-term effect on durability of this. We know how cement is working. We know that when we build with cement, we can, when we make concrete with cement, we can ensure 100 years of life, but even maybe even more. And so these solutions need to be studied. And replacing concrete is not the solution either, unless we want to go back 500 years in time. So our industry believes that this two-step approach that I mentioned before, the mitigation and the sequestration of carbon, is the right way to go. And this is not something that we are doing alone, but that we are doing with all our stakeholders. First is from the design. Designers should be able to optimize the building of concrete using, for example, high-strength concrete. It has been demonstrated that the higher the strength of the concrete, the lower the CO2 emission per square meter of structure built. And using tools like digitalization, which will also provide a way to reduce the use of concrete and better use concrete. From the raw material side, for sure, first cement industry. You know that out of the CO2 emission from cement, half is coming from energy more or less and half is coming from material process. Material cannot be phased out completely, and that's the small part that we have seen in the graph below, the small part that you cannot get rid of, but on the energy one, you can arrive until 100%. And also on the aggregate side, in terms of recycled aggregate and artificial aggregate. As precast manufacturers, well, we have to build, to design and to manufacture elements with circularity in mind. As I mentioned, long service life is the key one. Easy maintenance and repair, easy disassembly, either for use or for recycling, and keep on innovating, doing better structures, leaner structures, replacing maybe steel with other kind of reinforcement with low CO2 impact. And finally, there is also a role for the society, the stakeholders, and the policymakers to recognize what are the concrete benefits. Because yes, concrete is using cement. Yes, cement is producing CO2, but building with concrete, you get so many other advantages in terms of energy efficiency, adaptation to climate change, health and safety, places, and value to the local economy. But as I say, this is not sufficient. We also need to apply a strategy of removal. That can be done in two ways. The first one is an external one, capturing CO2 with different processes at the level of cement manufacturing. First, by concentrating the CO2, and then either by storing it or by reusing it. And this is not science fiction. There are already plants that are built at an industrial scale. This one is an example from Norway, for example, where this is today studied and applied for the future. But there is also an internal capture of CO2. For those of you who knows concrete, you know that concrete carbonates, it absorbs CO2. Theoretically, it's up to 85% of the material process CO2. I don't believe this is going to go until that level. But a recent study from Nature basically say that every year, the concrete which is in the world absorbs 50% of the CO2 which is emitted every year by the cement industry, because there is so much concrete, and this concrete carbonates that it is something that is happening. And this can be done actively, for example, by curing in precast factories concrete with CO2, but also, as I said, passively, naturally, it's sequestration of CO2 during the lifetime, and also by concrete at the end of life when it can recarbonate. And finally, second point is sustainability. Well, we believe that here concrete has a good position, because from the social point of view, it can respond to societal challenges. You probably know that it is foreseen in 2050, 70% of the human population will live in cities, which means high-rise building, try to reduce the soil occupation, and for this, concrete is probably the best solution. It provides health and comfortable places to live, and safe and resilient in terms of protection of the people. From the economic point of view, concrete contributes to growth, both in manufacturing and in the construction. Studies shows that for every euros that you put in the concrete industry, there is a multiplier effect of 2.8 euros on the local economy, because concrete is a local material. You probably won't get so many advantages for material than for concrete for the same price. And that's very important, because we don't want that sustainable buildings are only for a limited number of people. Sustainable buildings should be for everyone. And as I said, very important, the local aspect of the concrete industry. I think, if I remember correctly, the figures from France, I think that the radius of delivery of concrete is around 20 to 50 kilometers. And finally, for the environment, concrete is made with natural materials, mineral materials, no dependence on oil, no need for fire protection, no need for other preservatives. It has the very important property of energy efficiency, thanks to its thermal mass, and it also provides solution for a climate which is changing. For example, protecting city and the environment from floods. And when we look at the circular economy, I like always to use this inverted pyramid approach, where the first objective should be minimization and prevention, followed by then reuse and recycling, and ending with try to phasing out energy capture and disposal. In minimization and prevention, concrete has the big advantages of durability. As I said, the longer you stay in the ecosystem, the better it is. Easy to maintain and repair, and also new concretes are developed today that will further reduce the use of material for the same function. In terms of reuse, you can reuse the structure. Again, when a structure is lasting for 100 years and after 20 years you want to change the use of it, it's very simple with concrete. You keep the structure and you just change the non-load bearing part. But also product reuse, and that is something which is also studied here. But this has been done from, as I mentioned before, from the point of the design. The design should be done in a way that concrete can be disassembled and reused later on. And recycling, for sure, both for geotechnical works and for recycled aggregates. And here, let me make a point, very, very simple. When you have a road and a building to build, don't use recycled aggregate for the building. Use it for the road. All the work which is done with unbound aggregate in geotechnical works, that is much better to use recycled aggregate because of the remaining binding capacity of aggregates coming from a recycled concrete. And don't consider that using recycled aggregate for geotechnical works is downcycling, because the aggregates, the recycled aggregate, when they are used for a geotechnical work, has additional properties, better properties than virgin aggregate because of this remaining binding power. So, as a conclusion, as I say, I wanted to stick within my 50 minutes. We believe that our industry is able to provide solutions to the challenges of 2050, low carbon, sustainable, and circular economy, but also to other societal challenges that maybe today are not that important, but that we believe that may be important as well in the future, in particular adaptation to climate change. So, I believe that precast will be the backbone of a transition to a low-carbon construction 2050 and not an obstacle. Thank you very much for your attention.
Thank you very much, Alessio. Our next presentation will be by Eleftherios Pourdakis, who is the project officer for the European Commission, and he's been the project officer for the I RE4 project since 2019. So the floor is yours.
Good morning, everyone. I'm the project officer of I RE4 in this last part of the project life, so I'm very happy to be here with you and learn more about the project. The construction and demolition waste is one of the most heavy and voluminous streams in the European Union, and it accounts for 25 to 30% of waste streams in the Union. In the figure we see the circular material use rate, not only construction but in general. The Union is improving, but we see that there is a linear but minimal improvement, so we need to do much more in order to meet our targets. And the graphs show, let's say, some good examples and some countries that are lagging behind, so that we can see that there is actually a big span between the performance of the member states. And actually, there is a very interesting case of Luxembourg really going down the opposite direction of what actually we want to see. The European initiatives in legislation addressing construction and demolition waste is a bit fragmented, but not as fragmented as in other cases. All these initiatives come from the Construction 2020 strategy. We have the Waste Framework Directive in 2008 that, in relation to the construction and demolition waste, says that the member states by 2020 should have at least a minimum of 70% of non-hazardous construction and demolition waste prepared for reuse, recycle, undergo material recovery. In 2011, we have the Construction Product Regulation that says that the construction waste must be designed, built, and demolished in such a way that the use of natural resources is sustainable, and in particular ensuring the reuse of recyclability of the construction works, their materials, and part after demolition. If in case you are not familiar with the legislative terminology, a directive is a document that sets a target, like the 70%, and then it's up to the member states how they will reach this target, while the regulation is a legal document that the member states have to adopt as it is. So in the second case, this enacting term is a part of the national legislation of all member states. A few years ago, and the Construction and Demolition Waste Protocol and guidelines were published. This is not a legal binding document. It's just it includes a list of good practices that some member states followed, so that it gives incentives and inspiration for other member states, some good examples that they should follow in order to improve their performance on the field. Alessio already gave a very good presentation of the European Green Deal. It's one of the 6 priorities of the new Commission, and I would dare to say that it's our flagship for the next 5 years. We want to have an impact in all aspects, so that all the legal documents that will come out the forthcoming years will actually be binding by the Green Deal and should be connected to it. Some of the ideas that maybe have an impact on the construction and demolition waste is the proposal to have to recover the economic value and avoid or minimize the impact on environment and on climate change when waste cannot be avoided. Consideration of legal requirements to boost the market of secondary raw materials with mandatory recycled contents, and of course construction is among the sectors that will be examined. A universal proposal of an EU model for separate waste collection that of course may include the construction sector, and the sustainable products policy supporting the circular design of projects, focusing on resource incentive sectors, and again the construction sector is among those that will be included. Along with the communication document, a roadmap with some legal proposals that will follow the coming years was published. As you can see, it's quite time intensive. Most of the legal actions will be launched in 2020 and in early 2020, so that we can finalize the procedure as soon as possible. Keep in mind that usually these procedures are quite timely, including in the beginning an impact assessment study. Then when the document is an initial version is published, then we have a public consultation, votal approval by the parliament, then the trilateral negotiation. So usually the case takes several years in order for a document to become finalized. So some of the actions that will affect the construction and demolition waste are the proposal for a European climate law that will enshrine the 2050 climate neutrality objective, so that member states will be bound to that target no matter what. Then a universal circular economy action plan, as Alessio mentioned already. A proposal for a carbon border adjustment mechanism for selected sectors so that we avoid carbon leakage if we implement strict targets for example, in this sector for cement and steel companies in Europe, so that we avoid companies moving their production outside the EU and then importing the materials. Initiative to stimulate lead markets for climate neutral and circular products in energy intensive industrial sectors, and propose a legislative waste reforms. All this should come in the very near future. The Reinventing a New Way to Build is our proposal for R&D in the construction sector, and of course it has an impact on the construction and demolition waste field. For those you are familiar with Brussels, you may recognize in the left picture our headquarters, the Berlaymont, built 50 years ago. And the right picture is a picture I took from my office, and we see that not much has changed in those 50 years. So we still, most of the construction is done on site. We still see those cranes, and the equipment more or less is the same. And actually I took the picture on a typical Brussels rainy day, so workers were outside in the rain doing all the field work. The construction sector is one of the most important sectors in the EU, accounting for 9% of the European GDP. It provides 18 million of direct jobs, and by 95% it consists of SMEs, which is a very important factor for the European economy. Unfortunately, we see that a very low digitalization progress. Most of their firms do not utilize their full potential in digitalization. This figure shows what are already the established technologies in the construction field. So we have the BIM, for example, maybe not in as broad as we would like to see. We have some off-site prefabrication, project scheduling, material management, recycling, and so on. And then our Reinventing a New Way to Build has 4 pillars. The first one, of course, is digitalization, so that we support a more digitalized construction sector. Modularization with robotics, 3D printing, and so on. And then the last 2 that are more related to your field, research on materials and related to circularity. Digitalization would include BIM, digital twin, AI, and so on. I'm not going to go into details. This is not the subject of the workshop. Modularization could have an interest for your field. It includes 3D printing, robotics, and prefabricated elements. But then the circularity and materials could have recycling of materials, materials management, new materials with lower carbon footprint, prefabricated elements made out of recycled materials, so that the ultimate goal is that we achieve a circular economy in the built environment. We are now preparing the work program for 2021-22, the first 2 years of Horizon Europe, that is the successor of Horizon 2020, and addressing the construction and demolition waste is part of the projects, the calls that we are considering, but since it's a work in progress, I cannot share more information for you, but hopefully later in the year you will hear more from us on the field. Thank you, and if you have some questions, I will be happy to hear.
Thank you very much for your presentation. Our next presentation will be on use of CDW from the architect point of view, and the presenter is Paula Vioria, who is the professor in the subjects of construction at Universidad Politécnica de Madrid. The floor is yours.
Thanks. So good morning, everybody. My name is Paula Villori. I'm a professor from the Technical University of Madrid, and I also participate in the Building Technology and Environment Research Group of the School of Building Construction. The title of the presentation is Use of Construction and Demolition Waste from the Architect Point of View, and I will explain some strategies to implement circular economy principles in a building project. I've divided the presentation into 4 parts. I will start with a brief introduction explaining the current situation of construction and demolition waste and the negative environmental impact of our industry. I will then continue highlighting the main principles of a circular economy, and I will highlight the best practices that we can use to reduce the waste during the design phase of a building. And I will end the presentation with some conclusions. So we already know that the human emissions are already changing our climate. Unfortunately, it's very common to see these pictures that we see on the slides showing natural disasters that are constantly occurring worldwide, from melting poles, storms, hurricanes, or flooding areas. And the construction industry is one of the major human activities causing this natural disasters. The construction, as I say, generates negative environmental impacts and is responsible of 40% of the carbon dioxide emissions generated in the European Union and 50% of the water consumed. It's also responsible of consuming 60% of raw materials and around 30% of the waste generated. If we focused on the construction and demolition waste generated in our sector, we can specify that over 400 million tons of construction waste were generated in Europe, which is a huge amount of waste, but that's not the only problem. The problem is not only the amount of waste that we generate, but also the management that we do for this waste, which is in turn around 50% as an average of the total waste that it's actually recycled. This means that there are some member states that is recycling over this 50%, and other member states are well below, following a linear economy of making, using, and disposal. So this means that there is a significant loss of valuable minerals at the end of the process. So we cannot continue hiding. We cannot continue looking to another part. We need to act. We need to make action of our work, and we need to implement several strategies to try to tackle this problem and try to reduce the amount of waste that we are generating. Instead of reducing the natural resources, generating and creating waste, why don't we imagine our buildings to make the world a better place, instead of existing in conflict with the natural environment? That should be our goal, actually. So in order to move around this 50% of an average, we need to switch this percentage and try to work towards this 100% in order to achieve this total success in our sector. So for this, many European initiatives have been launched, as for example the circular economy, which is one of the initiatives, European initiatives, which promotes recycling and recovery of the materials. This circular economy principle is based on 3 strategies. The first one is designing out waste and pollutions. So for this, the buildings should be designed and optimized for disassembly, eliminating the concept of waste and re-entering these secondary resources into the economy as valuable and technical resources. As a second principle of the circular economy is keeping the products and the materials in use as much as possible. So for this, we should use products or materials that can be disposable. This means non-toxic, and that can be safely returned to the biosphere. And also durable materials that we can reuse as many times as possible. The third principle of the circular economy is regenerate the natural systems by using energy required to fuel all this cycle should be renewable by nature, by using solar or wind technologies, renewable energy whenever possible. But our question should be, how can we reduce from the design phase of the building in order to achieve a zero waste generation? Well, we have several strategies over the different stages of the life cycle of a building, and I'm going to focus only on the design stage. So for the design stage, several initiatives or strategies that we can use will definitely promote or reduce the amount of waste generated in the construction stage. So we can group the different strategies into 5 main concepts. So for the first one, which is designing our building for deconstruction, this means design the building to manage its end of life in a more effectively way. So designers should definitely use materials and construction methods which allow a deconstruction process and promote reuse and recycling. Several strategies can be used. For example, minimizing the number of the different materials, the different connections and components of a building, designing the joints that should be accessible and durable, using mechanical joints instead of other type of joints with adhesives that cannot help to disassemble the structure at the end of life. Using non-toxic and durable and high-quality materials that can be reused, avoiding binders or adhesives or secondary finishings, and our important part, which is developing a deconstruction plan during the design process. So when we design our project, we are already thinking how we're going to disassembly. A second aspect to be considered is the adaptability and flexibility of the building. Buildings should be designed in order to allow to change the function in the future, and this can be done by designing open spaces or regular shapes of the building. We also need to focus on design to standardize, to have a modular designs in order to avoid different complex shapes, which will generate more waste and will also difficult the deconstruction process. Also, using prefabricated materials will help us to achieve this zero waste goal. We also have to take in mind that we need to design for waste prevention. How some strategies that we can use is using some waste management plan templates or waste prediction tools, which help us calculate or estimate the waste generated that will be generated. They usually also have some minimization strategies during the construction and the design phase of the building and estimate some costs. Another best practice would be to avoid a surplus of materials in the design phase and also in the manufacture and order of the materials during the construction phase. Keeping the products for longer or more durable and reused when possible. Using less hazardous materials and also promote the use of prefabricated materials. And another best practice would be promote construction systems which generate less waste. So for this, in our research group, we developed a project called Waste to Resources that was funded by the Spanish Ministry. And this project had the goal to analyze the waste generation in building energy efficiency rehabilitation works. And these works were mainly focused to increase the insulation of the building. So several different strategies or actions were evaluated, and the total waste generated was calculated for each of them. As conclusions, we saw that these techniques performed from the inside of the buildings will generate less waste than those performed from the outside. And among the techniques performed from the exterior of the facade of the building, in terms of waste generation, the ventilated facade, so the ethics would be without removing the external existing coating layer, were the preferred solutions. Another strategy is to minimize the design changes or errors. This it's a complicated task, but it can be tackled from the beginning if the projects are detailed and if there is a good coordination between the different agents that will be involved later on in the project. Also, avoiding design complex details will also reduce the amount of waste generated. And another important aspect, which is increase the coordination and communication among the different agents involved in the design and in the next stages of the construction, will also reduce the waste. This means that the information of the building should be updated, the revision should be quick, and should be also quick distributed. For this, BIM methodology will definitely help to increase the coordination and communication with the rest of the agents involved. And also, we plan in advance the waste management that will be used on site through best practices. We will also reduce the amount of waste generated. For instance, some best practices that could be planned in advance could be estimating on the tracking of construction and demolition waste, or managing the reception or collection of the materials, depending on the construction site needs. Following the manufacturer's instructions regarding the transportation and storage of the materials will reduce the breakage of materials on site. And fundamental, one of the most highlighted best practices is the training of all the actors involved in the construction and demolition waste management is indeed one of the best practices highlighted by the actors. But what's the point of recycling if there isn't an end of use of the waste generated? This is an important question. So for this, it's fundamental to design and to promote strategies to use recycled material in the projects. So for this, using materials with high recycled content will be a good practice, as well as reuse materials within the same construction site or near construction. For this, it's important to detect which activities during the construction can incorporate reusable materials from the proper site itself or others which are near. But despite there are many research and development publications and projects that are aiming to characterize several materials incorporating construction and demolition waste, or even other waste from other industries. The reality is that all this information and all these documents are not really reaching the society, because there is a lack of implementation in building projects. One of the research project from the UK highlighted some of these reasons that could be uncertainty on the durability of recycled materials and products, a lack of standards concerning the use of recycled products and their performance, the recycled material suppliers and products is difficult to find. And there is a poor perception of construction professionals about recycled materials. They believe that the products are inferior. And this is something that when I teach with my students, I always ask them to have a picture in their mind of what's a recycling house looking like. And they always answer the same. Well, it's a house with recycled bottles of glass or wood, and we need to change that. We need to change that mind towards a more technological houses which we can build. So it's important in order to overcome these reasons of a lack of implementation. It's to develop standards to assure the quality of the recycled products, as well as the minimum technical specifications for recycling materials. And also for the architects during the design, it will be very helpful to have a catalog of recycled materials and to collect information regarding their performance and the environmental parameters. So, well, as a conclusion of my presentation, I think that achieving a zero waste target is a highly challenging target for the construction, and we need to involve and to commit all the stakeholders that collaborate and in order to reduce the waste and to develop efficient waste management strategies. Definitely, the use of bin technologies, of tools, will help to involve all the agents and can take the industry closer to the zero waste vision that we are looking for. Thank you very much for your attention.
Thank you very much, Paola. Now we'll move to the next session, which is about innovation with international dimension. And Alessandro Largo, the project coordinator of the RE4 project and the head of the Resilient and Sustainable Civil Engineering Unit at CETMA, will present the project. The floor is yours.
Thank you.
Okay, thank you very much, Susanna, for your introduction, and thank you very much to you all for being here and attending this workshop related to innovation and circular economy in construction. My special thanks to guys from Acciona, Pepe, Maria, and guys from Phoenix, Susanna and Philip, for this very nice organization. My special thanks to our new project officer, Eleftherios Bourdakis, as I know it's not that much easy for you to move from Brussels, so it is very much appreciated for us to be here. And also thanks to the presenter that have already presented, to Alessio, Eleftherios, again, Paola, because you gave a very nice overview of what is needed in the construction sector. And today I will introduce you the RE4 project, that is a project of circular economy in construction. And before I get to the heart of my presentation, I would like to briefly present CETMA, that is an Italian RTO founded in 1994 and located in Brindisi. Our main premise is Brindisi, but we also have another office in Milan. Our skills are related to materials engineering, industrial design, and ICT, and our industrial priorities are materials and constructions, transport, productive systems, energy, and healthcare. Coming back to the RE4 project, it is a project of circular economy in construction, which is accounting to the last available key figure from the FIEC, one of the main drivers of the European Commission, of the European economy, accounting for more or less 10% of the gross domestic product, with 100 billion of turnover and 6.5 of total employments. However, construction is also one of the main responsible of the main waste stream across Europe, which is construction and demolition waste, or CDW, accounting for more or less 800 million tons of CDW production per year. The most important thing is that a lot of materials coming from construction demolition waste can be recycled, but they are very often confined to low-grade application or landfilled. Another interesting point is that there are a lot of materials coming from construction demolition waste which are glass or wood or plastics with a very high recycled potential that is unfortunately unexploited so far. In this scenario, Europe has set the challenge of the development of an energy-efficient building concept by using new or adapted prefabricated components and allowing the reuse and the recycling of different materials and structure while reducing energy use and minimizing environmental impacts. The EU also set the target of a minimum share of recycled materials in the final product of at least 10 to 15%. This challenge was taken up by the I RE4 project that proposed the development of a fully prefabricated, energy-efficient, easy dismountable and reusable building made of concrete and timber components containing up to 65% by weight of CDW-derived materials and structures. To reach this goal, we have gathered a multidisciplinary consortium of 13 partners from 7 countries across EU and 1 non-EU country, made of 5 academic partners, 7 companies and 1 association. We also propose a very massive demonstration activity with 4 demos, 3 in Italy and 1 in Taiwan. With more or less 5 million euros of budget, the project started in September 2016 and it will end on February 2020. There are 4 main pillars that supports the project. The first 2 are technical and refer to the recycling and the reuse of construction demolition waste. In terms of recycling, we have proposed innovative solution in terms of sorting in order to increase the quality of CDW derived aggregates. As we know, that's one of the main constraints for growth is quality of CDW materials, that it is not always good enough when compared to virgin materials. This has been supported with a strong compliance assessment in terms of geometrical, physical, chemical and durability assessment, and lead to the definition of new quality classes with the aim of supporting the development of new standards in the field. And finally, the recycling potential of CDW materials has been verified through the development of several types of materials and prefabricated components and elements incorporating up to 95% of recycled materials. We know that in terms of reuse, we have to start thinking before the construction of the building, because we cannot try to reuse the building if it has not been thought to be disassembled and reused. That's why we have developed several types of disassembly strategies in order to reuse concrete and timber components from buildings that have reached the end of life. And we have proposed innovative design concept for prefabricated elements and an innovative design concept for a fully prefabricated, easy dismountable I RE4 building by using reversible connection, and this building is flexible enough to be easily tailored to different requirements, both climate requirements or structural requirements, for example, seismic requirements of different kind of countries across Europe. Those are the pillars in terms of the technical pillars, but we know that it is not enough if we want to push Europe to the forefront in terms of CDW management. That's why we have also taken other non-technical barriers like CDW management, for example. This has been done through a strong stakeholder engagement since the very beginning of the proposal, and also through the development of a BIM decisions support tool. This is our support to the digitalization of construction. This tool will provide an estimation of the quantities of materials that can come from a demolition, with possible option reuse and recycle, also taking into account logistic references in terms of the construction site, in terms of the company that can process these materials and use it to build new components. We hope that this new approach may create new attractive business opportunities, as well as new young technical profile, like for example the CDW managers. And the final pillar is related to the end user perception, as we know that people do not want to hear about materials from waste. That's why we have proposed a strong performance assessment in order to verify that precast components may incorporating high ratios of CDW performs at least in a comparable way with respect to traditional components. And we are also proposing certification and standardization strategies for this new type of components. Also a life cycle analysis to demonstrate that the new components have less environmental impact with respect to traditional one. HSE analysis in order to demonstrate that these new solutions are safe enough, at least in the same way as traditional solutions are. And finally, we are providing several types of training videos for students or for new technical young profiles. In terms of achievement, the project is fostering the transition from a linear to a circular economy in construction, and that is why we have provided different kind of solution at different level of the CDW management value chain, also taking into account the European CDW management protocol, which has been already introduced by Eleftherios, and which I suggest you to have a look if you have not already done, because it is a very inspiring document that provides a lot of tips and inspiration to understand what is really needed in order to support the transition from a linear to a circular economy. In this slide you can see some of the results that we have achieved so far. For example, in terms of CDW identification, source separation, collection, we have provided the RE4 deconstruction strategies and the RE4 design for 100% reusable building. In terms of logistics, we have provided the RE4 digital tool that can support all the steps of the deconstruction and recycling and reuse process. In terms of CDW processing and treatment, we have developed innovative sorting system for high quality CDW derived aggregates. And we have also proposed new quality classes for this kind of materials in order to improve and increase their use in the final components. We have industrially produced several kinds of precast elements incorporating high ratios of construction demolition waste, and we also provide an assessment of different kind of CDW management and sustainability strategies across Europe. So if you ask me, it is possible to build a fully recycled house. Maybe Alessio will not agree with me, but I will say yes. In principle, it is possible if you take care of all the steps of the construction process. That's what we have done, and we have gathered all the solution we have developed, and we were able to build 4 pilot buildings, 2 for new construction and 2 for refurbishment. In this slide, on the left picture, you can see the pilot building that was erected in Spain with the lead partner Acciona. It's a fully prefabricated, 100% reusable building made of precast concrete and timber-based precast components. After the workshop, you will have the chance to physically see this building, and this will probably be the last chance that we have, because it will be dismantled in a couple of weeks in order to validate also the RE4 deconstruction strategy. On the right, you can see some picture of the construction process. The second building was erected in UK. On the right picture, you can see the final shape of this building. This is not a pilot. This is a real building, as it will not be dismantled, and it will be used for new labs and offices for our partner CREA. And on the left side, you can see some steps of the construction process again. In this picture, you can see 3 other pilot buildings. On the left, you can see a demo that was erected in Italy, and with main aim of improving energy efficiency of existing buildings to the application of a ventilated facade. In the central picture, you can see a demo in Taiwan that was constructed with the aim of protecting existing building against earthquakes and typhoons. And on the right, you can see another demo that in Italy that was related to the seismic qualification of the RE4 solution. It was a mock-up tested on shaking table to compare seismic behavior of the RE4 solution with respect to traditional ones. So, facts and figures of the process of the project. We have provided one set of statistics in terms of CDW management, 5 lessons learned, and 4 recommendations. 4 new technologies in terms of deconstruction, sorting, CDW management, and reversible design. 6 solutions at the material level. 1 is the proposal for new quality classes. We are in touch with several standardization bodies, and we have provided all the results that we have, because we hope we can support the definition of new standards in the field of CDW. And we also developed 5 CDW-based materials, normal and lightweight concrete, both with ordinary Portland cement and alkali activated binders, with different workabilities, self-compacted concrete, vibrated concrete, semi-dry concrete, and earthen materials, incorporating up to 80% of construction demolition waste. Then we developed 8 types of components, prefabricated components, 4 components and 4 prefabricated elements, concrete and timber facade panels, load-bearing concrete elements, internal partition walls, incorporating up to 80% of recycled material. And finally, we were able to provide 4 pilot buildings, 2 for refurbishment and renovation, and 2 for new constructions. In terms of achievements, we have also tried to disseminate and share as much as possible our results through events like this one, but also through our social media and the website. Moving to conclusion, the RE4 impact. On the left graph, you can see what it is, where the EU needs in terms of CO2 reduction, embodied energy reduction, and the replacement of virgin material with the recycled materials. And on the right, you can see the RE4 answer. We were able to provide more than 40% reduction of CO2 emission with respect to the request of a 30% reduction. We provided a reduction of embodied energy of more than 45% with respect to the request of 20%, and we were able to replace more than 50% of recycled materials with respect to the request of 50%. Moreover, we were able to provide an additional impact. It is an economic impact because the RE4 solution provided to be less expensive than traditional one of more than 50%. So to conclude, the RE4 project has demonstrated that construction and demolition waste derived materials and structures can be effectively reintroduced in the production cycle of concrete and timber components, with replacing rates in the range of 50 to 85%. So a fully prefabricated 100% reusable building is a reality now. So the way is paved, but there is a strong need of improved waste identification technique, separation and collection and source and quality assessment, and above all, policy and framework conditions that can effectively foster the transition from a linear to a circular economy in construction. Well, that's all from my side, and I will be happy to reply for any question during the question time. Thank you very much.
Thank you very much, Alessandro, for presenting the RE4 project. Now we will have presentation by Jamie Moreno, who is the Materials and Processes Engineer at Tecnalia, who will present the VEEP project, which is a cluster project of the RE4 project.
Yes. Thank you, Susana. So, ¿dónde está esto? Okay. So thank you very much for inviting us to this interesting event. I am Jaime Moreno from Tecnalia. I work in the Eco Materials and Circular Economy Group. Tecnalia is a technological center organization located in the north of Spain, in the Basque Country. So in my case, I'm going to talk about a similar project, European project. In this case, it's the VEEP project. And the concept is quite similar to the RE4. So the aim is to recycle the construction demolition waste and to manufacture new precast concrete component for new building. Okay, so in my case, I'm going to talk more about the technical result, and in order to demonstrate that yes, we can build a fully recycled house, or try it at least. So the VEEP project started 3 years ago, 1 year after the RE4 project. So we are now in the last year of the project, in the demonstration of the solution. The budget was about 5 million euros, and we are 15 partners of 7 different European countries. The coordinator is Anna Parabossi from Rina Consulting from Italy. And the VEEP concept, the VEEP objective is to fully close the loop of the building materials, starting from the production or the demolition of a building, developing new technologies for the recycling of those waste, from the product recovered from the new technology. We developed different new materials, eco materials, and with those materials, the material were almost concrete and aerogels for the thermal insulation of the new product. The new product were 2 kinds of precast concrete element. So for new building, for new walls, for new facade, and for the refurbishment of old facade. And now we are in the last stage, in the demonstration stage. So the final stage is the demonstrating 2 demo cases, the solution performed in this project. Okay. In this case, the objective was to replace at least 75% of the raw material by recycled material. So we are in the next step of the RE4 project. I'm going directly to the result, to the technical result. So the project started with the development and upscaling of technology for the recovery of different waste material. The first technology is a combination of air drying technology and heating air technology for the recovery, the release and improvement of end-of-life concrete. This technology is only for concrete waste, not mixed waste. So the aim of the technology is to separate the different fraction of the concrete waste. After a demolition, when we recover the concrete waste, in most of time the waste is wet, so we cannot sieve the material and recover the different fraction of the concrete. So the first technology apply a kinetic energy to break the bonds formed by the moisture, and we are ready to separate the coarse fraction from the fine fraction. So the coarse fraction is directly employed in new concrete, and the fine fraction needs to be improved, or needs to be improved in another technology, because it contains a lot of moisture, a lot of water absorption, and a lot of impurity that have to be removed in order to add the value of this fraction of material. So the fine fraction, we developed another technology, a heating air technology. So this technology applies air at high temperature, at 500 degrees, in order to remove all the moisture of the material, the impurity. It burns the impurity of the material, and it's also separate the ultrafine particle from the fine particle, the zero for the sand fraction to the ultrafine fraction. So the product obtained from this combination of technology are coarse aggregate with reduced impurity and water absorption, fine aggregate with also reduced water absorption and without impurities, and ultrafine particle that will be employed as cementitious material, as supplementary cementitious material, in order to replace the cement of the concrete formulation. The second technology was developed in order to improve emerging and minor construction and demolition waste, like the glass waste and mineral wool. So those wastes are very complex to recycle because of their properties, and we don't have for the moment any technology for the upgrading of the wastes. And the partner in charge of this technology have scaled in the project the wet grinding technology. This technology is a combination of grinding and compression for reducing the size of this material, in order to employ the fibers and the glass as an admixture in new concrete formulation. Okay, so from this technology we obtain microfibers and glass admixture in order to provide new properties to the new concrete formulation. For example, the microfiber will reduce the shrinkage, and the glass powder will improve the consistency of the fluidity of the concrete. Okay. And the third technology is a technology for the synthesis of new aerogel materials. So from silica-rich waste, we arrived to obtain a new generation of circular superinsulating material, new aerogels. So now we cannot employ aerogels in the construction sector because it's very expensive, and it increases a lot the cost of the precast elements. So with this technology, we arrived to reduce 40% of the cost of the process, and we obtain a new aerogel blanket for the insulation layer of the precast concrete element from construction and demolition waste. So, for example, in the project we employed silica-rich concrete made at the beginning with siliceous aggregate, and we extracted the silicic acid from this waste, and we produced new blankets, new aerogel blankets for the insulation layer. So with the recycled material, we developed different eco materials. So the first one was an eco cement. In this case, we tried to replace a part of the cement with the ultrafine particles recovered from the HASS technology. So in this case, we tried to replace directly 3, 5, and 10% with this recovered material, and we tested in cement pasted and mortar pasted the hydration of the cement and the compressive, the mechanical behavior of the mortars. So in this case, we observed that when we replace the cement up to 10%, we arrived to accelerate the hydration kinetic of the cement at early age, and we arrived to increase the compressive strength of the cement, of the mortars made with the cement. So answering to the statement of Alessio at the beginning of the workshop, I think, yes, we can reduce the environmental impact by replacing part of the cement by new addition coming from waste. So this eco-cement was also employed in new eco-concrete. So the eco-concrete was manufactured with more than 75% by weight of recycled material. So we employed 100% of eco-cement with 5% of replacement of the cement with ultrafine particles. We replaced 100% of recycled aggregate, both coarse and fine aggregate, with recycled concrete aggregate. And we also employed glass admixture and microfiber admixture in order to reduce the wrinkage of the concrete and improve the consistency of the concrete. So at the beginning, we optimized the concrete at laboratory scale here in Spain, Tecnalia and Acciona. And after the challenge was to upscale the production to a pre-industrial scale. So when we optimize a formulation at laboratory, it's not easy, but the conditions are controlled, and we can control the production. But when we upscale the production of the concrete, it's always very complicated because of the mixing process, and the operating condition are very different, and normally the properties of the concrete are quite different. So the challenge here was upscale the production to an industrial scale. And the pre-industrial demonstration was performed in Italy and the Netherlands in a precast company. So here you can find some result of the hardened property and durability properties of the new concrete. So we observed that, for example, the compressive strength was improved at early age because of the addition employed in the formulation. And the durability was also improved compared to the reference one. So we have developed a new concrete with more than 75% of recycled material, and we are right to improve some of the property of the material compared to the natural one. So the most difficult in this kind of materials is the durability. Is to obtain good, satisfactory durability properties, and in this case, the water penetration and the carbonation resistance was lower than the reference one. The third material developed in this project was the aerogel blanket. So in this case, the blanket, the aerogel was synthesized from 100% of recycled material, of waste, and we have produced more than 100 square meters of blanket for the insulation layer of the new precast concrete element. So the properties of the blanket, of the aerogel blanket, was similar to a commercial one. So we arrived to produce circular blanket, aerogel blanket, similar to the commercial blanket with a natural, made from a natural material. And we are right to reduce 40% the cost of the production of this kind of material. So at the end of the project, we have the objective is to demonstrate the precast element produced with the eco materials. So we have firstly performed different prototypes of the final precast concrete element. We have two types of precast component. The PC1 is for new building, for new facade, and the PC2 are smaller pieces for the refurbishment of all facade. So the PC1 is a multi-layer element with an external and internal concrete layer, recycled concrete layer, and an internal insulation layer that replaces the conventional EPS material with the new aerogel blanket. And the second one is only, well, it's also a multi-layer, but it's only composed of an external concrete layer and an internal aerogel layer. And in this case, the concrete layer was performed with lightweight concrete in order to improve the thermal properties and reduce the weight of the pieces. So we performed different prototype of 1 square meter of pieces, and we performed different tests in the concrete and in the prototype. So in this case, we apply the fire resistance test to the elements. So the result was that we are producing precast element with concrete with more than 75% by weight of recycled material, with a layer of insulation performed with aerogel, with circular aerogel, and we arrived to transmittance value lower than 0.17 watt per square meter Kelvin. Okay, and the classification to fire resistance is more than 4 hours of fire resistance. So, also comparing to the RE4 project, the pieces are also eco-designed in order to dismantle them after the use and to recover the different layer of the precast component. So now we are at the last stage, at the demonstration stage. So I think they are building now the mock-ups with the panels. So those pictures are in the demo park here in Acciona, but we are also performing the demonstration in the Netherlands, in other demo park. So I think this afternoon you will see also the mock-ups of the BIP project, and you can compare the different solution of the RE4 project and the BIP project. So now the next activity are similar to the RE4 project. At the end is to monitor the temperature, the different parameters inside the mock-ups, and to compare them with a reference mock-up that you can see in the back of the picture, the reference mock-up, in order to compare the solution, the new solution, and the traditional systems. Okay, so at the end of the project, the panels will be dismantled, and we will recover again the concrete, and we will perform again a new concrete with this material, in order to demonstrate the circularity, the full circularity of the process. So as a conclusion, we have developed three new recycling technology for the recovery of different wasted, the concrete, emerging construction demolition waste, and to produce novel and advanced silica aerogels. We have developed also 3 eco-materials, eco-cement, eco-concrete, and aerogel blanket with high amount of recycled material. And with this material, we have performed 2 types of precast concrete element. And now we are demonstrating the solution. So, answering to the question, it is possible to build a fully recycled house? Yes, I don't know if yes is fully recycled house, but we can arrive to it in the next future. Okay. So thank you very much for your attention.
Thank you very much. Now we'll have a coffee break, and we will come back with more presentations. We will start at 12 o'clock, so feel free to grab some coffee and talk. Welcome back. We are now moving to the session for circular economy in practice. And unfortunately, Andrea from ZRS didn't make it, but Alessandro will present her presentation and tell you a few words about how to design a full recycled and reusable house.
Thank you again, Susanna. Before I start, I would like to apologize because most probably I'm not the right person to do this presentation, but I think it might be worth to provide some hints about the RE4 design, which is one of the another great achievements of the project. So I will speak. This is the first time I see this presentation. So, but if you have any question, Andrea is on her way to come here. So you maybe speak with her about the design later on. So this is the overall idea of the RE4 project. The idea is to take materials coming from the RE4 sorting system, divided by type, so bricks, tiles, stone, glass, wood, plastics, and clay, to develop new materials with this type of recycled materials, and at the same time to take components from the demolition and to reuse components from the demolition, and then to integrate new prefabricated components made of construction demolition waste and reused elements into a fully prefabricated and fully reversible buildings. To do so, we have set a list of indicators for the easy installation and disassembly of prefabricated components, and those indicators refer to modularity and variation in size, providing intelligent system that offers repetition and interesting architectures, to easy of assembly and disassembly through the use of reversibility, reversible connection, lifespan, durability, easy of repair and maintenance, to foster a long-term duration of the RE4 buildings. We have also fostered the use of material simplicity, so prevent the use of composite materials to enable future recycling, as we know that composite materials are very hard to be separated and then reused. And also other indicators that we look at were transportability and traceability through the BIM database for future reuse. In terms of design, those are the lifespans of building elements that were chosen. In terms of structural components, more than 100 years. In terms of thermal envelope, more or less 50 years, and in terms of interiors fittings, less than 20 years. We also take care of the seismic concept, and the assumptions we use for the calculation are reported in these slides. Material properties coming from the characterization from test results that we performed on the RE4 materials and components. Dead loads were chosen according to designed build-up code of elements, and live loads were chosen according to the code requirements and most demanding local conditions through Europe. And finally, local culmination was done according to the Euro codes. In terms of dynamic loads, siphoning systems, a dual systems was chosen to have a compromise between flexibility and the use of complexity of the connection systems. We also fostered the use of modular building, as you can see in this picture, because modularity, regularity, and symmetry may facilitate the use of structural parts at the same time ensure a favorable dynamic behavior. In this slide, you can see some of the elements. I don't know why we have this red dot here, but you can see in this picture, you can see the skeleton construction with the stiffening core. In the central picture, you can see the non-load bearing ventilated vapor open facade, and on the bottom picture, you can see internal partition walls, internal solution with high thermal mass. Those are some options for layout floor. As you can see a lot of flexibility, adaptability of the solution that can be easily restructured to fit different requirements, architectural requirements. And then we use a reversible connection, because if you want to reuse, to take component from a building and reuse it, you have to allow this to be easily done. And the current way for do this to use a reversible connection. Here in this picture you can see reversible connection for columns. These are a reversible connection used by our partner CREA during the manufacturing of precast column. And here you can see some information related to beam to column connection, as you can see here. Again, the connection for facade panels. So mechanical connection are used instead of the traditional connection that are grouted. This will ensure an easier removal of these components, and this will be validated in February, maybe, Maria, through the dismantling of the Spanish mock-up. In terms of energy efficiency, the design fostered the standards, the current European standard, and for concrete panels, we provided solution to obtain a U value of 0.192 watt on square meter Kelvin, and for timber panel, the U value was set at 0.15. This is our last goal, because it's okay from a technical point of view to recycle and reuse materials, but a solution should be also appealing, and those are two solutions that were provided by our architects for a easy dismountable, fully prefabricated RE4 building. That's all from my side, and this is the presentation related to the design, and hopefully Andrea will come in later today, and you can discuss with her about any detail you want to discuss about the design. Thank you very much once more.
Thank you, Alessandro, for stepping in. Our next presenter is Ruben Correa from CREA Concrete. Recently designed and detailed the new concrete laboratory facilities for the company as part of the RE4 project using CREA's concrete precast system.
Thank you, Susanna. My name is Ruben Correa. I work in CREA Concrete Products and have been coordinating the CREA efforts in the RE4 project. Today I will speak about the challenges, developments, and achievements in the manufacturing of RE4 prefabricated structural elements. But before I start with my presentation, I just want to do a quick introduction to the company. CREA Concrete was established in 1976 and has become one of the largest producers of concrete products in the UK and Ireland. Through knowledge, innovation, and the willing in delivering new solutions, the company has become market leaders in the sector, and today operates from its main offices in Tunbridge, Northern Ireland, but has bases in Scotland and England as well. The company is committed in delivering a large range of quality products, from which I can highlight the SPENTERM, isolated flooring system, and the RapidRes, which is a fast-track precast building system suitable for multi-story buildings, which the company designs, manufactures, and builds. CREA Concrete also offers bespoke precast solutions, and today has a large range of different sorts of precast elements, with different shapes and finishes in its portfolio. Returning to the subject of my presentation, the RE4 structural elements are reinforced concrete precast walls, sandwich panels, beams, columns, slabs, and stairs. We used concretes for these elements containing up to 100% of CDW-derived aggregates to replace the virgin aggregates, and this translated into elements with up 80% of CDW content. During the project, two design approaches were used. One, a fully reusable precast frame system, which uses bolted connections, as Alessandro's shown, and a second system based on the rapid race system by CREA, and which uses grouted connections. For both systems, all the elements were manufactured at CREA Concrete, and they are suitable for fast-track modern methods of construction. During the project, because all the elements were made of reinforced concrete, a lot of effort was put into getting CDW concretes with high levels of CDW, and this was achieved by our partners at a lab scale. Now, my thanks to RISE, QB, and SECMA for developing great concretes that when we upscaled them just after a few trials and small adjustments, those concretes were ready for full production. And the structural elements, we use 3 concrete, a self-compacting concrete for casting solid elements horizontally, a semi-dry concrete mix for the hollow core RC slabs, and for the production of stairs, we used a vibrated concrete. One of the main concerns when dealing at the industrial scale is the supply of quality raw materials. And in the case of the CDW, we identified several challenges, mainly related with variability and quality in the supply, possible contaminations, and segregation when stockpiling the CDW aggregates. Based on our knowledge and experience dealing with new raw aggregates, we specified some procedures to deal with these issues when handling the CDW materials, so that there was no safety or quality issues during the manufacturing process. In the development of the RE4 structural elements, as mentioned, a lot of effort was placed on getting the right concrete, but also the design and the production planning. The structural design of these elements was accomplished by several partners, CREA, Acciona, and University of Naples. After the structural design was ready, individual detailed drawings were produced for the production teams to be able to plan the manufacturing process, especially on how to place and fix the connections, the special connections used in the RE4 project, and how it was possible to reuse the molds during the entire manufacturing process. Here I show you some rebar and mold drawings where we can see the level of detail required by the production teams. All the elements were produced at CREA facilities, where we use steel tables to give the concrete the best finish possible. These steel tables are heated and are kept at 20 to 25 degrees to give adequate temperature for the concrete to cure and to have good strength development. In the cell production, we use inclined molds, and that's why we use the vibrated concrete for the production of stairs. To mention that the steel tables are vibrating tables, and they can tilt to help with the casting and lifting operations. Now I'll guide you through the production process of this element. With the exception of the hollow core slabs, all of the structural elements have an identical manufacturing process, which starts with the steel reinforcement, where rebar meshes are bent, cut, and welded together according with the production drawings to form a steel cage. At the same time, molds are prepared. These molds are made of wooden shutters placed against the steel beds, and they form a formwork to cast the elements. After this, the steel cage is inserted in the molds, and they are ready for to receive the concrete. The concrete is produced at on-site batching plant and transported to the factory using a lorry. On arrival, the concrete is sampled and tested for flow or slump. If approved, the concrete is discharged into a 2 cubic meter skip, which is used to pour the concrete into the molds. I have here a small. Here we are seeing the casting of the outer layer of a sandwich panel. Once the concrete has hardened enough in the molds, the finishing works can start, and they can be done manually or mechanically depending on the project specifications. Then the elements are left to cure until they reach the minimum required strength for lifting, which in this case is 15 megapascals, and usually happens within the initial 16 hours. Before the molding, the concrete is tested to check the strength of it, and if approved, it's molded, lifted, and transported to an adjacent area where the final finishes and quality inspections are carried before the elements are signed off and sent to site. When it comes to the home span, which is the trademark name at Korea Concrete for the hollow core RC slabs, the entire process is done in an automated facility where only one worker is required during the entire operation. The casting starts with placing the steel bars into a steel mold, and the concrete pour is done using an automated discharge system. I have here just a small video. During the entire process, the mold vibrates because we are using a semi-dry mix. The molding of the slab is done ready after the casting by rotating the mold into a rack. I also have here a video. I hope it works. I'm not too sure if you can see in the video, but at this point, the pipes that form the hollow cores are being removed, and then the mold is lifted, leaving the slab in that rack. this process is only possible using semi-dry concrete. After this step, the rack is lifted and placed to cure in an adjacent area. Once it achieves the required strength, the slab is pushed from its rack into a conveying system that transports the slabs to outside, where the final inspections and storage is carried out. During the entire manufacturing process, we check the quality and test the concretes. Here I'm showing a table of the results of the CDW concretes used in this project, and we can see that all the concretes performed very well. They achieved the lifting strengths within the normal curing times, and they achieved the target strengths at 28 days, with the self-compacting concrete and the vibrated concretes performing better than we anticipated. From all the manufacturing and quality inspections, no major issues were noted. As said, the concretes performed very well. Just some small brownish stains were observed in the panels after a few days of storage. This probably is related with the silt and clay content in the CDW, sands and gravels. But this won't affect the performance or the application of finishes such as plaster or paint into the elements. Finally, the structural elements were successfully manufactured. Here you can see all the elements produced for the 3 demo sites in the UK, here at Acciona, and in Italy, where the seismic test was performed. And as an overall conclusion, I can say that the RE4 structural elements are comparable to standard concrete precast products. And here in the pictures from left to right, we can see a wall, some slabs, hollow core slabs, and columns, and more RE4 products, load-bearing sandwich panels, beams, and stairs. And this is all from my side. Thank you for your attention.
Thank you, Ruben. Our next presentation will be on other RE4 building elements of the non-structural type, and the presenter is Linus Brander from RISE, Sweden, the research institute.
Yep. Thank you. Hello, everyone. So I'm Linus Brander from RISE. Okay, this is the old. How do you do this? So, and I come from RISE, which is short for Research Institutes of Sweden, which surprisingly is located in Sweden. So it's the largest research actor in Sweden. So, is it on? Ah, okay. Thank you. Okay, I got the honor to present other elements than the load-bearing concrete elements. And so just to start, this is the final image, actually, the achievements from RE4 when it comes to elements. Some slides, the upper ones you recognize from Ruben's presentation. They are from CREAG, and they are actually from the load-bearing concrete elements. And you also see below some examples of other elements like timber facade element and some insulation elements. So just to try to explain which kind of elements, they're quite diverse from different producers. So here you see the ones I'm going to talk about. One is a non-load bearing sandwich panel, which is actually it's a further development of the CREAG standard sandwich element that we have worked with at RISE and which has been upscaled at CREA. Then we have some other elements. We have extruded ventilated facade elements from Vortex Hydra in Italy. We have a non-structural timber facade panel from ZRS in Germany. And we also have a wood insulating panel from Setma. So all of these rely to create these and to achieve these high replacement levels. It's dependent on good sorting, good separation of CDW to receive clean fractions. So as you see here, to the left, you have incoming CDW. In the middle, you have a typical recycling plant from CDE, our partner in crime. And to the right, you see ideal fractions, different material fractions that you can use for different type of things. For example, wood fiber fraction, which can be used for insulating panels, or aggregate or mineral fraction, which can be used as new aggregates in different types of concrete. So I will start with the RE4 insulating panels made from by Setma. So this is a thermal insulating soft panel with no binder. So it actually, you see the process starting from upper left with 100% CDW wood fraction, which is molded into a soft panel. So, and during many different trials made by Setma, varying different parameters, they finally came up with an ideal process for this at 160 degrees Celsius for 4.5 hours. So this is 100% CDW and no binder, and these soft panels, they are also recyclable. Next, I will do this quite quick because I can't say too much of every different elements, but since we all have representatives from Setma, Vortex, ZRS, soon I hope Andrea will come, and also from RISE, you can ask us more about if you're interested in particular elements. So the extruded facade panels. This is based on an existing concept by Marmorock in Sweden, with which Vortex have a commercial agreement to produce this. And the main, since this is an existing system, the main goal in RE4 was to use CDW as to replace the sand. So this, in this mix, this concrete mix that is extruded as panels, it's roughly 70% of that is sand. The remaining is cement and water. So of the sand fraction, in different trials, Vortex tried to optimize the replacement level. 100% didn't quite work with the CDW mineral fraction available due to some problem with the extrusion, but at 85% they achieved good results. So in the project, in a preliminary upscaling, creating panels for testing, Vortex succeeded in making 42 panels using CDW mix, and also produced several panels for the final demo buildings. So jumping to the timber facade panels. Here you see design, not too much, too many, not so easy to see maybe, but the panel is roughly 5 meter long, 2.4 meter high. For this purpose, of course, this can be adjusted depending on what need you have. And you see also cross-section, and the width of this is, of course, can also be adjusted according to the hydrothermal requirements at the place of use. So this is a... and here you see in short, the process from a pile of timber, CDW timber, which you notice from this pile, this doesn't come from a recycling center, because of course this is not a small fraction. So this is reclaimed directly from by selective demolishing of existing buildings. And by assessing the timber, by identifying damaged areas, metal fittings, and other things you don't want in your recycled timber, you prepare and cut in different way and plane this material and construct. And in the middle you see this sandwich panel in construction. And I also think you see Andrea. She's the one missing that Alessandro gave presentations, and now at least you have seen her, part of her. And upper right, you see the final timber facade element, which is consisting of 95% reused and recycled materials. You see the soft insulating panel sticking out in upper right. Here you see some steps that I mentioned in assessing and producing this from the waste timber to the final product. So I will say a little bit more about the non-load bearing sandwich panel, since I've been more directly involved in that one and therefore know a little bit more. So this is a very rough layout of the conventional sandwich panel made by Creag, and which was used also for the load-bearing sandwich panel Ruben told you about. So the difference here is that from the conventional is that we, exactly like in the load-bearing, use CDW-based self-compacting concrete in the inner layer, but in the outer layer, instead we use a high-performance concrete based on CDW. And we also have a textile reinforcement instead of steel reinforcement. By this we can reduce the thickness of the outer layer with half. And this and the fact that we don't have steel reinforcement in the outer layer reduces the weight of the entire panel with approximately 20%. So some images here in the upper left, you see the outer layer being cast, you see the carbon, you see the mold, and you see the carbon fiber textile. And it's casted with high performance concrete, and then you have insulation and steel reinforcement for the inner layer in the second image, and in the final image you have the casting. And this is images from the preliminary upscaling at Creag, in which we, from laboratory, made a first upscaling to produce test elements. And we tested this, for example, as you see down to the left, with 4-point bending strength, and supervised it with digital image correlation to see how the stress was distributed and how this element corresponded to this testing. And based on this, the real upscaling of the elements meant for the demo building were performed at the factory. To the right, you see a cross-section of the panel with insulation. You see the outer layer with the carbon textile reinforcement. You see some steel reinforcement in the inner layer. So, and to say a little bit more about how we made this when it came to concrete. Of course, first you have the CDW, you need to assess the quality of it and test it. And that's, of course, the first task. And we did that in many different laboratories, not only RISE. And when it comes to these self-compacting and high-performance concrete, then you obviously start with some kind of mixed design you already have, but you try to optimize by replacing as much as CDW as much as aggregate as possible with CDW, but still keeping the requirements of the industry. So for example, CREAG, they had requirements on us for a certain slump flow, workability, and also, of course, strength development and final strength. And then we also, for this outer layer, for the high performance concrete and the outer layer of this particular panel, we also made several tests at RISE to find the optimal textile reinforcement, because there is not only carbon fiber, you can also have, for example, glass fiber. But finally, we stuck for the one layer. Some final remarks to end this. I want to say a little bit about the quality of CDW. Almost every type of CDW, even though if it's mineral fraction like you see here, or if it's the wooden fraction, or if it's plastic fraction, the quality of it will affect how much you can use in your new materials and components and elements. So with mineral fraction in concrete as example, this is example of two different materials we worked with. We worked with, I think, 12 different batches from different parts of Europe during the project, but this is an example of two. The one to the left is much cleaner, so if you divide it, if you want to access its composition from different materials, you just divide it in different piles, weigh it, and you get the distribution. So without more detail, you can understand, okay, the one to the left is quite clean, because most of it is unbound stone or concrete particles. The one to the right is much more diverse. You have a lot of bricks, you have quite a lot of bituminous material, and so on and so on. So two different materials, and of course this composition of the materials will also influence what properties it has, physical, mineral, chemical properties the material will have. So below you see there is an existing system you can use in the concrete standard EN 206, classifying the material in two different classes, type A and B. And using that one, these materials classify as type A and type B. Type A is better. And also, when we're working with this, trying to optimize use of CDW with respect to the final properties you want from your concrete. This is the replacement level, for example, for HPC, high performance concrete, we achieved using these two different fractions. So for the high performance concrete, using the aggregates or the CDW to the left, we achieved 90% replacement, whereas we had to lower our ambition levels quite a lot with the one to the right. And this really stresses the importance of good sorting, good separation in order to receive clean fractions, and that will substantially increase the quality and hopefully also the economic value of these fractions. So to conclude, almost every time it's quite, you can make a lot of these different CDW waste streams, but it's very clear, not only from this concrete example or the mineral fraction, that you need to adopt your mix and your ambitions with respect to the quality. So quality systems are very important to assess for these type of materials. But overall, we think this is quite good results that confirms the robustness of the RE4 system, that even in high technical TRL levels, being able to replace quite a lot of the material. So, thank you. I think I stop there.
Thank you. Thank you, Linus. Our second to last presentation will be presented by Maria Casado from Acciona. She's been working as a research and project manager in the concrete group.
Hello, good morning. Thanks to all for coming. I'm Maria Casado and I work in R&D department of Acciona Construction. My talk is about how to build and disassemble a fully recycled and reusable house. From a practical point of view, based on the demonstration activities of the I RE4 project. So how could we build and disassemble a completely recycled and reusable building? The I RE4 project addresses this challenge through the design and development of solutions for modular and easy assembly and disassembly of eco-friendly prefabricated elements. Modular and easy assembly means to use prefabricated construction instead of on-site construction. Easy disassembly means to design for the construction, paying special attention to reversible structural connections. And finally, eco-friendly elements means to develop building elements with construction and demolition waste materials. Here you can see an overview of the demo sites. This slide has already been presented by the project coordination, Alessandro. We have different demo sites, both for new construction and also for refurbishment. Concerning the solutions for new construction, these I RE4 solutions have been demonstrated in two different climate scenarios. In a cold scenario, through a pilot demo building in North Ireland and a second pilot demo building in Madrid. Concerning the solution for refurbishment, we had two different demo sites, one in Benevento in Italy, another in Taiwan. The objective of demonstrate the RE4 elements in Taiwan is also to demonstrate the high replication potential of the RE4 solutions outside Europe. Starting from the demo from Spain, this demo is the one we will visit later on. Here you can see the demo building. This building is built with prefabricated components. All the facade elements are designed to have a U value of 0.30 watts per square meter Kelvin, which is much lower than the U value required by the Spanish legislation, which is 0.66 watts per square meter Kelvin. And this building has been designed as a two-story building with a concrete frame of a single column and 4 beams with a set of bearing and all bearing prefabricated wall elements. Here you can see all the RE4 elements and components that has been installed in this demo building, between wall panels, both structural and non-structural elements, wall panel, beams, columns, solid floor slabs, sandwich panel, block buildings, facade, a timber facade panel, a timber internal partition wall, a ventilated exterior wall cladding made with insulation boards and extruded tiles. The replacement rate of the virgin material by recycled material is range from 50 up to 100%. All these elements and this building has been designed for easy assembly and disassembly and reusability. That's why a lot of effort we have put to design, not to use, reversible connections. Here you can see all the connections we have selected for the demo building. All these connections are of the cell connections, mainly from Peico and Halfen. The wall to foundation connection was done through this type of anchor bolts. The name is wall shoe. The wall shoe was embedded in the wall, and bolts were embedded in the foundation. Concerning the connection between the column and the foundation, it's a similar connection. We use column shoe embedded in the column at the manufacturing stage, and then anchor walls were embedded in the foundation. Concerning the wall-to-wall connection, the corner between the two walls was resolved using this type of connection, which is a precast copper with a fixing anchor. Concerning the connection between the wall to the beam and the column to the beam, we use this type of connection that is a PC corbel. This element was embedded in the wall on the column, and in the beam was embedded the counterpart, which is named PC beam shoe. And finally, the slabs were supported by one side on the panel through the steel plates, and on the other side, this slab has a L section, so they were supported to the corbel side of the beam and fixing with anchor bolts. Here you can see all the elements produced by different partners. Here you can see the wall panel, beams, columns, and so on. Also, we have the timber elements. You can see the facade element, the internal partition wall, wood insulation panels, the extruded ties, the foundation, and you can see all the connections embedded at the fabrication stage of all the prefabricated components. So here you can see the PC wall, the wall shoe, and in the beams you can see the L beams and the square beams. These are the sandwich panels, and this is the foundation with embedded anchor bolts, and so on. In this video is a short video about the construction steps of this RE4 building. Besides the RE4 building, demo building, we have built an additional reference demo building for comparison purposes. This building has the same geometry and volume as the RE4 demo building. The objective of this demo building is for comparison purposes in terms of construction times, construction cost, and energy efficient properties of both mock-ups. This building has been built using traditional construction techniques in Spain and conventional materials. That's why this building was built with cast-in-place concrete frame, and The exterior, the building facade was made with concrete blocks covered by the traditional system usually used in Spain, composed of a layer of sturdy polystyrene insulation of 4 centimeters. This polystyrene insulation was fixed on the was fit by polypropylene fixing pins. Then, after the polystyrene insulation, a fine layer of polymeric regulating mortar was added. Then we place a fiberglass mesh, and finally the regulating mortar and the primer and the color mortar. This building was designed to have a U-value of the walls of 0.66 watt per square meter Kelvin, which is the value established by the Spanish legislation. All these buildings, both buildings will be dismantled next month in order to show or to compare the dismantleability process of the prefabricated RE4 building and the on-city construction of this building. And these buildings are currently being monitored. You can see some sensors places. These are surface temperature sensors placed to measure the temperature on the surface of the buildings. Concerning the construction times, this building, the reference building, took to construct, including the exterior and the internal gypsum plaster and so on, the stairs and the windows, 36 days. Against 14 days, it took to build the RE4 prefabricated building. Moving to the second demo, to demonstrate the solutions for a cold climate. This demo from UK. This demo was, here you can see some pictures of the demo building. As you can see, this is a real building, it's quite big. It was built with prefabricated elements, with incorporating recycled material up to 85%. The U-value of the walls, the U-value calculated for the walls is 0.20 watts per square meter, which is quite good. This building was made with load-bearing sandwich panels, and then internally, the internal partition walls were made with concrete blocks. The elevated floor was using the home span slab, which is an element very commonly used in UK and in Ireland. That is a hollow slabs, and then also in order to access to the first floor of the building, they have installed two stairs. This building has been designed for easy and cheaper assembly and not for reusability, because this building will have real use. This building will be the oral installation of Create in Ireland. So that's why in this building they use precast grouted connections. This type of connections include a combination of circuit details, embedded grouting pipes, embedded wire loops, and rebar with grouting joints with mortar and concrete. If you have some questions about this building, you can ask Ruben from CREA, or we have a representative of each demo site, so you can ask later on. In these slides, I'm going to show you the construction steps of this demo building. The first steps was to install the ground floor sandwich panels. On the second day, they installed, when the block walls were started to be built. The third day was devoted to install the first floor slab. The day 4, they focus on the joints and connections to seal all the joints and connections. And the seconds follow repeat the same steps with the first floor. So they, on the day 5, they install the sandwich panels on the first floor, then the floor slab, and finally they install the stairs, the roof and windows, and finally, after 14 days, they complete the RE4 building. Concerning the demonstration activities for demonstrate the solutions for refurbishment, this is the first demo from Italy. The selected element to be demonstrated in this demo site was a ventilated facade made with insulation with walls and extruded tiles as cladding system held together due to vertical and horizontal steel rails. This demonstration was designed for easy assembly and disassembly. In this demo, we use components with a replacement rate between 18.5 and 100% of construction demolition waste to replace the natural material. Here you can see the final aspect of the demo site. This is on your right. On your left, you can see the wall before the refurbishment, and on your left, you can see the wall after the refurbishment with the installation of the insulation material and the cladding system. The existing wall was made with autoclave aerated concrete, cement plaster, and finished base material on lime and cement. And after the refurbishment, with the application of the installation of the RE4 cladding system, we add 2 different layers, a buffet insulation, air cavity, and a cladding system, which is the tiles. And as you can see, this wall is currently being monitored, and the measure U value dropped from 1.1 watts per square meter to 0.24 watts per square meter, which is much lower than the value established by the Italian legislation for refurbishment, which is 0.4. To finalize, this is the last demo from Taiwan. As I said at the beginning of my presentation, the objective of this demo was to demonstrate and validate the high replicability potential of the RE4 solutions outside Europe. This demo site, the objective was to install 2 high-performance concrete panels with 40% of recycled aggregates replacing the virgin aggregates, and the installation and the manufacture the panels were designed for easy assembly and also to protect existing structures against earthquakes and typhoons. Here you can see some pictures on the bottom of the fabrication stage of these panels, the installations, and finally the 2 panels installed on an existing facade. All these demo sites are currently being monitored, and we will have all the results of the monitoring at the end of the project, which is next month. Thanks for your attention.
Thank you very much, Maria. The last presentation will be by me. And I would like to thank all the presenters for presenting all the parts of the RE4 project and the VIP project. And I would like to finish on a strong point with investment opportunities. This means some interesting numbers and facts about the markets which the RE4 project is addressing. So the common topic of the whole day was circular economy, and we know that it has been defined as industrial system that is restorative and regenerative by intention. And the three principles are to preserve and enhance natural capital, to optimize resource yields, and foster system effectiveness. Of course, there are more, but I have chosen these three to begin with. So let's now talk about the market potential. The RE4 project has three markets which are the most relevant. These are construction, retrofit, and prefabrication. So I will tell you some numbers about the European markets, mainly the construction market. So prefabricated housing demand is on the rise as building techniques are improving and they are leveraged by new house builders. The market is picking up across Europe. Here you can see the numbers of the forecast by Deloitte from 2018 to 2022. And also the acceptance of the manufacturing forms is increasing with the support of the legal process improvement, and further boost is expected. From the sustainability point, the interest is also on the rise, with the Green Deal and sustainability being a key word in Europe. Europe offers the biggest market for retrofitting, and retrofitting is one of the most cost-effective ways to reduce operational cost. The market is growing, so there is huge opportunity for the RE4 products and technologies to be placed on the market. And also the building stock is dominantly energy ineffective. There are many buildings which need to be retrofitted, and there are significant energy and heat losses all over. As we heard, the EU legislation is regulating the construction of new buildings and is supporting energy efficient renovation solutions, which leads to higher end user acceptance, which is one of the goals of the regulations and of the efforts by the project and by EU. The excessive amounts of the construction demolition waste are overburdening Europe. You can see the number of tons, which you have seen this number many times over the day. And RE4, among other projects, try to offer a solution and are offering solution. So to conclude this, the European legislation and the strategies of the EU are favorable for the RE4 technology and the solutions they offer. I would just like to show on this graph the CDW breakdown, which activities generate the most CDW, and you can see that the biggest portion is residential and non-residential demolition. So RE4 is really addressing this big portion of the activities which are contributing to the large amount of CDW waste. Here, just to run over of the SWOT analysis of the RE4 project. I will mainly talk about the opportunities because this is the point of the presentation. There is minimal competition on the European market. This project is unique in that it's complete and it focuses on different parts of the building and the whole building. There is a favorable regulatory environment. It reduces the consumption of raw materials. The entire components can be reused. It's energy efficient. The RE4 technology contributes to solving the issue with excessive CDW. And the market potential is large with existing and growing need for energy efficiency and the large amount of buildings in Europe that need to be retrofitted. And also the lack of new buildings. As we know, the number of new buildings is low and there is big demand for accommodation, so this is one of the solutions. Part of the potential is also replication. There are always some barriers in replication of different solutions and local conditions. So different conditions require different designs. One size fits all approaches cannot fulfill the needs of the involved stakeholders. But the RE4 design is flexible, as you have seen with the different demo sites, the locations. So it takes into consideration the different requirements. So the demonstrations in the UK, Italy, Spain, and Taiwan are the proof of that. And also Taiwan demo site opens the replication potential outside of the EU. So thank you very much. I hope we finished on a good note and you enjoyed the whole day of the presentation. Now I would like to start open discussion. One more note, if you didn't sign the sign sheet, the attendance sheet, I would like to ask you to do it after. And are there any questions? We will start with open discussion, so if you have any questions to anyone here, you can raise your hand and I'll pass you the microphone. Yes?
Hi, I'm Ignacio from Indra. I work with sustainable construction projects. I would like to ask, when are the facilities included in the project and how are they considered in the reutilization of the project? The mechanical, electrical facilities.
The mechanical installations, I don't think they were considered on the project. But for example, in the precast elements that we use, we can insert the pipes to pass the wires for electrical and pipes for heating and so on. Those can be established at the design stage and then cast in the elements during the precast manufacturing. I hope I have answered your question.
Yeah, thanks. I suppose so, but since it was not mentioned.
Yes.
Anyone else? We can also leave the discussion. We will have networking lunch, so you can ask. Yes?
Just a comment on this question. From our side, from DGRTD, we are having an open call for proposal on the topic. So the topic is about creating prefabricated elements for building renovation that should be complete. So they should also include mechanical part like ventilation, heating and cooling, and so on.
Thank you. Any more questions? Okay, so I would like to thank Acciona for hosting this workshop, then my Phoenix team for the support, and of course Chetma for coordination. And now we can move on to the lunch, and feel free to discuss and enjoy. Thank you very much.